welcome all of you again in the second part of the course Photogeology in Terrain Evaluation. So, as in the first part, we learned something about the theory of this course, and in the second part, we mostly learned about the applications of this course. Okay. So, application of photogeology in terrain evaluation. So, in this part I am going to explain you some practical information, I am going to present some practicals on identifying geomorphic features and identifying some geological structures, some landforms related to coastal, aeolian, fluvial and other type of environments. So, in this lecture particularly I will move from the small scale images to large scale images. Like first I will show you a larger version of the Indian map, then we will move to some smaller areas. So, how to identify different type of geomorphical landforms and geological structures, or how to identify the deformation pattern and the impact of some events in the regions like some earthquakes, some tsunami, any sort of events. So, in this part first I will explain you about the subduction zones of the world. Okay. Then we will move to some particular regions like Indian Ocean, in that Sumatra Andaman subduction zone. Okay. So, let us go ahead with the first slide. So, these are the 4 largest subduction zones of the world. Most of know about these things. So, first is Sumatra Andaman subduction zone, second is Hokkaido Honshu, third is Cascadia, and the fourth is Chilean subduction zone. So, these 4 are the largest subduction zones. However, they also have some minor type of plate boundaries and which have convergence or divergence in between these 4 subduction zones. So, like here the blue line is indicating the convergence margins, convergent plane boundaries, okay, and this yellow line shows the mid oceanic ridges where the lava continuously erupt over the surface of the ocean in the submarine portions, and there solidify and form the ridges or rocks at these regions, which are called the mid oceanic ridges. So, that is why here the material which is solidified here, those materials are of younger age, and which are away from this region, those are of the older ages. So, this green, yellow and red colors are showing the ages of the sea floor. Okay. So, here you can see that green part is representing the older sea floor, and red, as you move towards the mid oceanic ridge you will find some younger material. Similarly, this blue line is indicating the convergence plate boundaries. So, here there is a convergence between the Indian oceanic plate and this continental plate, which is known as Sunda plate. Okay. Here this is the Himalayan range. Okay. So, I will show it on the broader view. So, what is meant by subduction zones? Here the maximum seismic activity is responsible for the large magnitude earthquakes. Okay. And on this map you can see the parts which are brighter, which have higher intensity of lights. So, those regions are indicating the zone of large magnitude earthquakes or the highest seismic activities. So, these are the earthquakes since 1898. So, this is the Andaman Sumatra, as I already explained. This is Hokkaido Honshu, this is Cascadia, and this is Chilean subduction zone. So, that's the reason for the large magnitude earthquakes along these subduction zones. Now, if you see the aerial coverage of these subduction zones, okay, like if you are having Google Earth access, then you can see these subduction zones on the Google Earth, and you can see the very prominent features along the subduction zones, where one plate is subducting beneath the other plate. So those prominent features can be easily identified on the Google Earth images also, because Google Earth images are the satellite images, and other types of satellite images like Landsat, IRS, and different types of satellite images. You can identify these because these are the largest features on the surface of the earth. Okay. So here this line is very prominent on this image. You know that this is the Indian continent landmass, this is the Indian oceanic plate, and this is Sumatra, this is Andaman Nicobar Island, Andaman and Nicobar. So this is the chain of Andaman Nicobar Islands, this is Andaman Sea. Okay. And this subduction zone, this red color subduction zone, is between the Indian oceanic plate and Sunda plate. So this oceanic plate is subducting beneath the continental landmass. Okay. So this continental landmass is continuous from here to here. This is, here you can see this is Burmese microplate, and this is Sumatra, here Malaysia, Thailand. So all these made up the Sunda plate. Similarly, this is another subduction zone, Hokkaido Honshu. Here also you can demarcate a very clear boundary between the oceanic and continental landmass. So this is the oceanic plate, and which ocean? This is the Pacific Ocean. This feature is very typical shape of the Japan. So Japan itself is a large island, but it's a country. So this whole island represents Japan, and the 2011 Tohoku earthquake and tsunami was resulted in this subduction zone and caused a very widespread tsunami that affected the whole country, and that was a transoceanic tsunami and affected all the surrounding regions along this Hokkaido Honshu subduction zone. Similarly, the third one is Chilean subduction zone. Here you can see the countries like Chile, Santiago, Argentina, and all these some US countries, and this line, which is very prominent on this image, this is the subduction zone. So this is called the Chilean subduction zone. This was responsible for one of the largest magnitude earthquake in the history. Another subduction zone, that is Cascadia subduction zone. Here also you can see some countries, some cities aligning along this subduction zone, that is Washington, Oregon state, and this prominent line here is representing the subduction zone. So how the subduction zones are formed? So suppose this is the continental plate and this is the oceanic plate, and this is subducting beneath this. So this region basically forms the subduction zone, and this point, this suture zone, this called the trench. Okay. As the Mariana Trench in the world is the deepest part on the earth's surface. Here you can see this is the Challenger Deep, and it is related to the deepest part of the earth, and the highest part, as you know, that is the Mount Everest on the surface of the earth. Okay. So on these satellite images, so we can easily identify the large scale features like subduction zones, the mountain ranges, the oceans and their transition zones, okay, and different type of environments like coastal environments and all that, with the help of some associated landforms and features. So now what happened during 2004? So why I am talking about the subduction zones? Because subduction zones are responsible for the largest magnitude earthquakes, and those earthquakes cause the changes in the landscape as well as changes on the surface morphology. So the names which are given here on this map are showing the areas which were affected in terms of uplift and subsidence and in terms of tsunami waves impact. So this Landsat image shows that the North Sentinel Island was uplifted because you can see here there is a gaining of some land, some new reefs or some new beaches and some shore platforms. So the island area shown in the first image is represented by the green color, and all other areas surrounding this green color was gained due to uplift, okay. So this is image of 2003 before the happening of 2004 event. So the earthquake occurred in 24 December 2004. So this was the image during 2009 of the same island captured by Landsat satellite. So in the similar way you can see another island, it is Kachal Island. This has some type of submergence, okay. This island shows submergence and it has lost most of the lands which are lying along the shoreline or the coastline, okay. So as you can note down here, the area of this island has decreased in this image, which was captured in 2005, and in 2014 it again shows that the area which was lost during the 2005 or post 2004 earthquake, so that is maintained here, okay. So now the GPS reading also shows that there is increase in the elevation vector, and that means the island is again gaining the land, okay, gaining its lost area. This is again the false color composite image of the North Sentinel Island and some other smaller islands. It also shows that it has gained the land. These white patches represent the fresh sand or the fresh sandy reef or beaches all along the original area in red color of this island. So here if I ask you, tell me what is the land level change here in this image, uplift or subsidence. So if you have an aerial photograph or a satellite image of a particular area, can you define in your terms, like where there is subsidence or uplift? So you can see here, as in the previous slide, when the island gains the land, then it means there is uplift, and when it loses the land, it means there is subsidence, and subsidence causes submergence, okay, because sea level rises and the shoreline moves towards the inland, due to which an island loses its area or land. You can see that this bridge was submerged after the earthquake, while this bridge is still there. It means that it is at some higher elevation than this bridge. Similarly, tell me, in this image, is there uplift or subsidence? So you can see here that the fresh sand is at the base of this island. So it represents that the shoreline must be there before the event. Now shoreline has moved towards the sea. So now this is the present shoreline after the event. So it indicates that this island was uplifted. Here again, like in the previous image, you can see the submergence of this area, due to which inundation causes the waterlogging into this area, and due to which the agriculture, farming and the settlements have been affected. Okay. Similarly, in this image you can see there is extension of the land. So here we can say also emergence of the land or emergence of the wave cut platform. Similarly, another oblique photograph shows the Indra Point at the Nicobar Island. This is the lighthouse, and before the earthquake you can see that it was surrounded by the lavish green vegetations and all the settlements, but after the earthquake there was a subsidence, due to which all the matter up to the present day shoreline was swept off. Also, most of the things were swept off during the tsunami, and the remaining parts of the vegetation and the settlements were gone up during the post seismic subsidence. Means the subsidence occurred after the event. Okay. So see the color photograph, again the aerial, oblique aerial photograph, which shows the original view of the colorful view of this area at the present day, how it looks like. So everything has gone. Okay. So these are the effects of the earthquake and tsunami, which you can map on the images or the satellite data, or if you are having some vertical and oblique aerial photograph, you can demarcate the boundaries of the affected regions, and you can prepare the hazard map on the basis of the past events and their effects in a particular region. So these methods and techniques are also very helpful for hazard mapping and zonation. So now let's move ahead towards mapping. So this is a SRTM image, and here if you look at this image, you can have idea of the most prominent features and the well known landmass like India. I draw the boundary of this landmass. So this will show the continental landmass, and this bluish part shows the oceanic plate. Okay. Suppose here there is a Indian continental landmass, and this is the Indian oceanic plate. So this is the continental plate, this is the oceanic plate, but there is no break between these two, because the land which is exposed above the sea level, those are the continental landmass or the continental plate, and the land which is below the sea level, that is the oceanic plate. This is the continental plate. Okay. Similarly, there is no break up to this point, but this, let's take another color. If you see this feature, this you can say that this is something, a gap between these two plates, because this is forming a deeper trench between these two plates. And how this is going? This is going like this. If you see the broader view of the world map, then you will be able to sort out this plate boundary. Okay. So this plate boundary is called the subduction zone. Which subduction zone? It is somewhere it is termed as Sumatra Andaman subduction zone, Sunda subduction zone, because the name of this plate is Sunda. Okay. So this is the Indo-Australian plate, because there is some Australian plate also. Okay, because this Australian landmass is here, somewhere here. So Indo-Australian plate, and this is the continental landmass. This plate is subducting beneath this Sunda plate. So this yellowish line demarcate the subduction zone, and this here you can see Arabian Sea, Bay of Bengal, Andaman Island, Andaman Sea, then 90 East Reach, Sumatra, Sunda plate, and Gulf of Tonkin. These are the geographic features on this image. So this image is processed in ArcView GIS, and the bathymetric data has been taken from the JEPCO. So what is bathymetric data? This, because the bathymetry is also highlighted on this image. You can see the ridges, the submarine ridges, okay, and all the features, elevated features beneath the Indian Ocean. Okay, and this map is called the shaded relief, eTopo. Similarly, this is an SRTM raw image of this region, which is covering from India, Arabian Sea to this part. This is Hokkaido Honshu subduction zone, this is Japan, and this is the Pacific Ocean. So now if you see this image, you will be able to extract only the most obvious information about the continental land masses and oceanic regions, but how to make this map more informative. Okay. So for this we have to trace the important features what we are able to look on this map. So here first we have to trace all the features to make this map more informative. Then we collect some other information about this region from other sources also, so that this map becomes informative and we can extract maximum information out of that. So digitizing, the word known as digitizing. Suppose if we are able to see the boundary of this landmass, then to highlight this boundary is called digitization. Digitizing the map to highlight this the boundaries which are obvious or which are doubtful but can be confirmed from other sources like Google Earth, some other satellite images. Okay. So after doing all this exercise, what we have now, look at this image. This is the same image in the previous slide, and now this is changed completely. You are able to demarcate all these things. Okay. On this image we are highlighting the information, and there is a separate layer in which we have digitized this map. So what is that layer? This is the layer. So this layer contains only the traces and the exercise what you have done to digitize this image or to make this image more useful and more informative. So how this has changed? This was like this, and now this has changed to this image. Okay. So moving ahead, this is a GigaBlue image, and you can use these kind of images for a more clear visualization of the landmass from the oceanic regions. Okay. And if you want to read the elevation information for the landmass, then you should go for some topo maps or some kind of the SRTA map, or the maps which are the images which contains the information of the elevation also. Okay. So lat long elevation. So by highlighting the elevation information, we are able to highlight the areas of higher altitude. When you see the image of Himalaya, so you will be able to see how, at what elevation Himalayas are and how they are differ from the planar areas. So this I will show on the Google Earth images in the next lab. So after reading all this information, so we can prepare the tectonic map also. So tectonic map means to highlight the information of the faults, including the minor faults as well as the large scale faults, and subduction zones, and the direction of subduction, and the some volcanic information, like there is some volcano or some other kind of tectonic feature like lineaments and folds. So all this information we can put combinedly on a tectonic map. So as for this region, you can see that this line, this red line demarcates the subduction zone, and these triangles are showing the direction of subduction. Okay. So if you see here, the direction changes a little bit. If you see here, the direction changes a little bit. So direction of subduction, and this is showing the spreading ridge. Spreading ridge means it's a sort of where the lands are becoming where the lands are separated from each other due to extensional tectonic regime. Okay, so here there is a presence of extensional tectonic regime, and this is Sunda fault, and you can see the sense of motion on this fault is like this. Okay, so this part is going up, this part is going down, and similarly you can see here barren volcano. There is a volcano around the middle part of the Andaman, and this is Andaman Sea. This is the capital of Andaman, Port Blair, and WAF is West Andaman Fault, and this is Car Nicobar, this is Great Nicobar, and this is the rate of subduction. So at this rate 15 plus minus 3 mm per year, Indo-Australian plate is subducting beneath the Sunda plate. This is the Landsat falls color composite image, and on this image you can also highlight some features, like here you can see a very linear feature is shown, that is the airport. This is the Port Blair airstrip, and this is here first the greenish part. Okay, let's move from the major to the minor. So the greenish part comprise most part of the image, which is the dense vegetation. Okay, it shows the dense vegetation and mixed type of jungles, and this part is forming a bay region, and here you can see there is a stream which has formed some water body. Okay, so stream ponding is also a common feature of the islands. Here also you can see the same thing, stream ponding and tidal estuary. There is a channel coming from here. So all these things combinedly we can map, and mapping all type of features like the mainland. Okay, these are the settlements. These pinkish regions are showing the settlements on this image. So we can demarcate all these very easily. So preparing such a map is called the categorizing geomorphic landforms or some land use map. So we can prepare some land use map and some geomorphic map with the help of this image. I am going to explain how we can do geomorphic mapping of this area. So suppose we take this region where we are interested to make a geomorphic map. This region is known as the Constance Bay. Okay, so these are the locations of our sites 1, 2, 3, 4. Okay, in the previous map I have shown the sites. So those 4 sites are located here. One site is also here. Okay, 1, 2, 3 and 4. Yes. So now here you can see there is a tidal channel going inside. So we are interested in preparing the geomorphic map of this region. So first we will classify the most prominent features on this map. Those are the coastal, the shoreline. Okay, the most prominent. So then we can able to demarcate the fresh sand part, which is the shallow oceanic region. These regions are showing the shallow oceanic part, and these are the deepest part, deeper regions. So these shallow regions we can classify like this. Okay, We can also map some wetlands here, some tidal channels, some wetlands here also, some channels and some ridges, like this is a ridge, this is another ridge, and this is another ridge. Here is some other minor ridge. Okay, so I mean to say, first we need to classify the major features, like which are very easier for us to demarcate. Then we can move towards the small scale features, like some small scale coastal landforms, cliffs, headlands, sea notches, wave cut platforms, like this. So with the help of this we can prepare such kind of geomorphic map. So as on the previous slide I explained, there is another thing which I missed on the slide, that is a narrow strip of beach. Okay, a beach must be following the shoreline. Okay, so there is a very narrow strip of beach along this island which is following the shoreline, so that we can also demarcate. So by combining all the features and all the information extracted on the previous slide, we can prepare this map, and we should also compare our geomorphic map with the topo sheet, because topo sheet gives the information of some contours and some prominent benchmarks which we can use and which we can incorporate while we are preparing our geomorphic map. So it is a combined approach by taking some data from the topo sheet and some data from the satellite images and some data from our own area, and from the photographs which we have captured during our survey. So in this map you can see that we have demarcated the deep oceanic areas, then shallow oceanic areas which also have the coral reef. Then these part are showing some lower elevated reefs, and these green ridges are at the higher elevation. So these are the higher ridges. Okay, and are forming some dense mixed jungle over the ridges, and here are some streams, and these regions are the wetlands, and so on. We will continue in the next lecture with some large scale geomorphic mapping, and will explain you how to map a region at a higher scale, okay, so that you can extract maximum information. So thank you so much.